people who want to, I'm doing a very lightweight demonstration just to illustrate the problem. For people who want to follow along, again, if you put the folder on the desktop, it'll be easier to do this. But basically, the problem that we look at in this latest bias paper, well, all three bias papers have had a central problem, and that problem is non-response. So imagine we have this little network here, and the brown nodes are nodes that have an out degree of 0, which practically speaking means they didn't respond to my survey, which makes me sad. And I now am stuck with the task of, well, I don't believe they don't have any links. I think that there might actually be links, but I need to recover them in some way. And so I can employ what we focus on in this paper is we employ imputation strategies to recover these links. I'm going to walk through one of them, but then I'm going to talk about a range of them, and I'm going to talk about how they influence various measurements of interest. Okay, so we have this network and we have an out degree of 0, but I can make a little model, and we were talking about ergon models last time. This is the simplest ergon model you can make. This is, I'm predicting my network using an edges term. Let me just sort of run this really quickly, and I'll do a summary. And essentially, if we look down, I mean, this is again where this having this very large R screen is somewhat difficult. What we see with this edges term is a log odds that an edge will occur. And then we can move that into, we can exponent that and get the proportion or the likelihood. And in this case, it's about a 4% chance in my model that I'll have an edge occur. Now we can simulate, and we're going to simulate here. We add a constraints term, and we say, well, I want every edge because I believe this information, the information I do have is correct. We can talk about if that assumption is a great assumption or not, but I want every edge that's in this network to be in my simulated network. And so I'm going to run this really quick. And now let me go and plot it, and we can compare this new network. All right. You can see now that many of my trouble nodes have edges to them. But we can also see that we have edges between nodes that were previously connected. Now, I'm going to tell you, based on this model, I'm not super confident in edges between already connected nodes because I've just included an edges term. We could, in the paper, we add a couple other terms. So we compare two imputation approaches with a modeling framework. And one of them is we say, well, hey, there's some homophily effect. And then there's, for directed networks, a reciprocity effect. And that would improve the estimates of the model. And we have a slightly fancier model. And we say, well, we think that triadic closure could be important. And we add a West term. And I have these notes in the presentation. But for the purpose of today, I'm going to say, hey, now I could do this, by the way. Ergons allow me to simulate multiple networks, but I'm going to do a post hoc correction just for purpose of demonstration. So I'm going to simulate 1,000 of these networks and get these little simulated networks. This takes a second or two to run. It shouldn't be too long. And the reason why I do that is this is a stochastic process. So I wouldn't take this one network as an indication of truth. What we really want is some distribution across many networks about, and in this, given this model, really about the edges that are connected to edges that have an out degree of 0, these brown nodes. Like I'm confident in the edges that exist. What I'm interested in is my certainty about the edges of these out degree of 0 nodes, these non-respondeds. Okay, so that's completed. This is just some summarizing stuff, and I'm going to create a little weighted network. And let's plot this distribution quickly. Again, this is just to give you a flavor of the kinds of problems. So, all right, what I'm looking at is for the edges that were not in the original network, was the distribution of basically ties that occurred. And for, basically, there's lots of possible ties. So over 1,000, you're not going to have this nicely highly peaked distribution. But I have more confidence in stuff in this latter tail than I do in things over here, right? So I can use that information, and I'm going to calculate the 90% quantile. And again, this is more just sort of an exercise about the logic of the thing. And I'm going to then threshold this network only on the edges for which we had no information. And I'm going to just sort of run through this to move to the slides and talk about more what we do with the paper. But to give you a sense, so here, this was the original network. This is the network with imputed edges over crowds and runs. But I only took new edges that I had no information about, like the ones for the non-respondents, but I kept everything else the same. Now, I could do a different strategy. So in the paper, we did not actually do this sort of additional post hoc thing. We had a model we had more confidence in, we had more information, so we had a Moffley effect, and we let that feature of getting some extra paths actually help us. But in this case, I was being pretty conservative. So let's get back to now the slides. Now that we've demonstrated the problem, which is we wanted to get edges back for non-respondents. And if I pull up my slides, go up a seek or two. So basically, what I was doing is a dynamic demonstration of these slides, where we're talking about, okay, we had we're going to talk about, we're trying to find these non-respondents. And Jeff actually, if you listen to the audio of this or have listened to my talk, we'll talk about, well, there's non-respondents E for which we had incoming ties. Those are pendants. And we had non-respondents like F for which we had no information. And the reconstruction methods. So now we're going to talk about different imputation methods that we use. Which we'll, let me come up and talk about. Actually, let me come up and, now that I've framed the problem, talk a little bit more about our setting. Okay. So we wanted to look at, all right, I've done this imputation techniques and I've sort of dramatized the problem. What are the impacts of imputation? What imputation strategy should I use that would be robust across a variety of settings? And so we took complete networks, empirical networks. We then basically took networks out. And this is a key thing I didn't talk about earlier, but I did talk about in my presentation, which is we had 3 instances where in one condition, we took nodes out and made them missing from the complete network at random. In another instance, we looked at peripheral nodes. And in another instance, we looked at highly central nodes. And the reason being is that nodes that have high centrality, if you remove those from the network, you can basically break apart the network. So they can, if you have those kinds of missing nodes, you can introduce a lot more bias. And then we applied imputation strategies, and we looked at measures of interest. And basically what we were doing is we were looking at the true network that we have, and then what we could recover back. So that was like the end setup at the end. Like, okay, we had this, well, except we have this underlying true network, and we just basically calculate this bias score. And we looked at networks for which we had only 1% all the way up to 70% missing data. Just to give you a sense of, so this highlights some dimensions that are important across these networks. Size is important. So we looked at small and large networks. Directionality is important. So we looked at directed, undirected networks. And also, what we found is sort of core periphery structures are important. And we picked empirical networks. So lots of this work does simulated networks. We wanted empirical networks because one of the intuitions is that a simulated network is hard to match. Like what? All right, is that simulation network really like my setting? But with these different empirical networks, you can go, okay, I'm working in schools, and my school is sort of generally this size, and it has this degree centrality. And what Jen was talking about earlier with these bias tools, you can put in characteristics, and you can get a sense of like, is my setting like this setting? So then to motivate a little bit, the measures that we looked at some degree-based measures, in degree, out degree, total degree, Bonsai centrality, closeness betweenness, and the centralization of those things. We define those in terms of the variance across the scores. And topology measures refer to to measures that we're looking at local structures. All right. So I want to talk now about the particular imputation strategies, and I guess I'll just use this here. So one strategy is list-wise deletion, which would be if I have no outgoing ties, I just delete them entirely. But if we look at here, that's terrible. They've lost a ton of information for this network. That's not a great solution. Another way to do this is to say, hey, I have incoming ties to these people that didn't respond. And I can either say, well, that's all the information I have. That's our asymmetric or directed approach. Or you can say, well, in many contexts, we think that they would be reciprocated. And so we can just binarize it or symmetrize the network and say, well, all right, we think that the information, it'll go both ways. Or this probabilistic rule is we say, what's the overall reciprocity rate across the network? And we can basically say there's a problem. We can pull from a distribution that's weighted based on its reciprocity. And we can then use that to make a little heuristic to inform if there's a tie or not. And I demonstrated later already these ergon ties, and I was trying to demonstrate the problem. So let's think about these in terms of measures. So we're often interested in degree measures. And one thing that we've found across all three of these papers is that in degree is pretty robust. Degree measures are pretty robust. So we have in degree, total degree. We don't have out degree. Why? Can someone answer to me why I don't have out degree? Probably. Come on, Jim. If nothing else, save me here. I'm not going to answer my own question. Yeah.
Because the out degree model we use is the data you happen to have.
Exactly, right? So it would have a perfect score. But if we're looking at, so we have these degree measures, we also have Bonsai centrality. And for people who are not quite familiar with, this is basically if total degree is you have power due to connectedness. Bonsai centrality says, well, actually, we should think of connectedness and power in distinct from each other, and that there's such a thing as relational dependence, right? So if you're highly connected, but like you can get your people you're connected to can go find stuff from other people, then we don't, your power over them isn't all that much. So we want to include Bonsai centrality as a relevant score here. And this is a neighborhood kind of approach. And why I'm bringing this up is we can look that in Bonsai centrality, let me summarize some high level things, right? So we're comparing these measures, we're comparing them across different levels of missingness. And I talked about this in my presentation, but just to remind people. So the negative 0.75 is highly peripheral nodes. 0 is random. 0.75 is highly centralized. The major takeaway thing I want you to take from the whole presentation is that in almost every case, doing something is better than doing nothing. Don't do listwise deletion. How do I know that? Because if I look at the listwise deletion line, almost all my lines are below, in most cases, that listwise deletion line. Now, with that said, there are definitely, well, there's one other high level thing I want you people to take away from this, which is that in many cases, if you do something, you got relatively low bias. And while in many cases, we find that, yeah, the model-based approaches are doing good stuff here in that they are the lowest line, they're also often very close to a less onerous approach. Like probabilistic often works well, and they're not always the golden solution. So in Bonsai Centrality, and actually, let me go to the next slide here, where we compare small and large networks and highly centralized and decentralized networks, the model-based approaches will often impute more ties than occur in reality. And while that can be helpful for getting back the truth in something like a path-based measure, in highly centralized networks where you have a clear core and then you have a clear periphery, it can actually impute ties that don't exist and create bias. So another thing I want you to walk away with is there isn't one clear-cut solution in every case, but do not despair. Because while it might be contingent, there is a logic. And I actually kind of want to skip down. Yeah, I think we can skip down. We can come back to particular measures and questions. So I just want to get to the logic, and then we can come back to particular cases and have people ask about it. So at the end of this paper, we give you a decision tree. And I want to walk through the decision tree in just a little bit of detail here. So the first question you should ask yourself if you're confronted with, I have these networks and I really don't, I want to recover some information and I don't want things to be too biased, is my network directed or undirected? Okay. The figure might suggest that in fact, undirected is more problematic because you see so many more nodes. Don't worry, it's actually not the case. Undirected networks are easier to impute back because essentially directionality causes a lot of complexity. The reason why the undirected side has so many nodes in it is that you just have more options. And the reason why you have more options is, because there's actually a little less complexity. But let's move to the next thing you should think about. So is it directed or is it undirected? The next thing is it highly centralized or is it relatively decentralized? And if it's highly centralized, then you want generally a more conservative measure, something like directed or probabilistic. And that's because it's not going to impute ties that don't exist. Well, the probabilist is a little bit more at risk, but essentially, so you're less likely to fill your space between the core and periphery with wrong answers. Then after that, it's the measure. And you should think about the logic of the measure. So degree is basically, how many people are connected to each other. And if it's a directed network, then that can be in degree, out degree. Power centrality has this neighborhood feature. And between the centrality and closest centrality are both path-based measures. To the extent to which we find that the model-based measures that basically recover a lot of paths do particularly well for between centrality and closest centrality if it's not highly centralized. But we also find that in a lot of cases, you saw overlapping lines earlier. There's a lot of instances where the simpler approach is almost as good or as good, or might even be better. And how that's signified in this decision graph is if you see only one node here, that means that's absolutely the best solution across all cases. If you see two nodes, it means that there's a less complicated and there's a more complicated approach, aka a model-based approach or one of these heuristic approaches, and they give almost identical results. They have overlapping lines. So that's why in the undirected case, we have this larger thing, because there's just basically the simpler imputation strategies often are working nearly as well or as well. Okay, so I've given like a high level thing. We can talk about particular measurement families. We can talk about particular contexts or situations. But I wanted to open it up for questions. And now that we've framed the problem and we sort of walked down sort of high level ways of looking at it.
Questions on missing data?
I can start with a pretty generic question for John. What's like the chief criticism that you see in papers when people choose to do imputation in the network field?
Oh, the chief criticism. Well, the chief criticism is they didn't do it.
Right.
And then right after that, okay, so one issue, I don't want to bore you with too much detail, but I will say some things when you're trying to navigate this. There's sort of some distinct literatures. And one of the things I think that's been nice about our papers is that we've actually been bridging some of them. So there's this reconstruction literature that uses these heuristic approaches to recover things. And then you have a really heavy duty simulation literature that's all about model, always going to the model. And so frankly, you're more likely, because they're pricklier, they're nice people, but they have opinions. The model-based folks will be like, well, why didn't you do this model? Like, hey, we have ergons of Sienas. Why didn't you cover it this way? Or why didn't you use a Bayesian thing? And part of that is, well, those folks often make an assumption that your network is just like theirs. Like that you're operating in a nice classroom that's reasonably sized, and you can reasonably do an ergon of Siena. Hey, on either, as a person that does stuff with really large networks, or Jeff, who's actually the head author, who does stuff on really small networks, you can't always make that assumption that it's all going to be a nice, like, bounded school environment. And so the criticism, like most often I get, is wanting people that basically modelers are like, oh, do the most complicated tool, when often actually you can do something simpler. And I think that, one of the opportunities of this body of work is getting more practitioners to talk about what are the problems that they're encountering, and that they need they need a solution that works for their context, given their data.
Thanks for that answer.
Yeah, I'd echo that. I think the other thing that it's an interesting question, because I think you don't actually see the critique of these things that often in published papers. Where you see them is in the reviewers' comments that say, like, fix it. And so it's the real damage done in the kind of models is that those papers just never appear in print because the reviewers have kicked it out for some reason or the other. So seeing successful examples of imputation models, I think, is still pretty rare in these network bits. I do think one of the things that we do see is that there's a lot more imputation for missing edges between a given set of observed nodes. Like, those models are much more common than a model that says, okay, we've observed a set of relations that are partially covered, like Tyler talked about, but that's only 80% of the school. I want you to simulate the other 20%, and that's or impute to the other 20%. And you see much fewer of that, because it is a difficult problem. If you find in all cases, I think with these kind of model-based bits, you have to assume that, and this was Tyler's point yesterday, right? You have to assume that the model has to assume that whatever information you have on the observables is generalizable to the unobservables at a high level. And that's just the necessity of the beast. I think that part of what would be nice to get, like, I would love to see models there, someone to work on models that do essentially design-based truncation sort of features, because the biggest damage done to most of these models is that we've had to, for survey convenience reasons, or to get anybody to finish the survey, we have to truncate the number of people they can nominate, and we know that's false. And so it's kind of remarkable that we see the results we do see, given that we've truncated these models so well. And so it'd be nice to know what happens if you assume that people's, in a principled way, that the the 11th, 12th, and 13th person, a person could have nominated but didn't. Can we impute that in a way that's respectful of the ordering of things? And I know that Alex and some of his students have done some work on this using the Amen framework, but I don't know if I've seen the results of that come out yet. So.
Yeah, hey, Shannon.
Hey, John, thank you so much for that. And I will probably come up with my real questions in about 3 weeks when it finally dawns on me.
I'm there with you.
I'll sound like the total novice that I am when I ask this. But so one of the things I really had a hard time with was translating this idea that oftentimes the way I think about these networks are that, so for example, if we were asking a survey on suicidality in adolescents, and so, it's a very highly centralized node in the network, and however, maybe a large group of kids don't answer it, either one, because they don't want to answer it, or two, because they don't have the symptom. But to impute what that is there any mechanism to say there's going to be other intents behind not having the data? So not that I just don't have it, but that perhaps
Yeah. So basically you're saying there should be other sources of non-response, essentially. And one of them might be the homophily term, because you could imagine that people that don't want to, well, it depends, obviously it depends on the question. It might, if it's stigmatizing, then the homophily term might not help you too much, because nobody wants to answer the question. But if it's a feature that you can imagine actually it impacts people in different ways that you can capture. So oftentimes we have roster data on the nodes, and we could look and say, okay, I think that this population might be at greater risk, and we might even be able to sort of model that look at that as a supplement to what we're doing with our network data, and we could include that maybe as a homophily term. So that would be one way of doing that. We actually sort of got this, Jim, I think when in the review of our paper, we had a reviewer that was talking about missingness, and was sort of pushing us on like, well, what about, and this is related to Alex's work, actually, like doing this dimensional model where you say, well, okay, how much of missingness is really because this person is in this place in social life across a couple of relevant dimensions. And again, in settings where we might have administrative data to actually construct that might be helpful. So we didn't do that kind of model here, but we have had reviewers that have brought that up as another thing to think about. And I think it's an interesting question.
Yeah, and I think that in terms of a question like, in a situation where you have a survey that you're then turning into a two-mode network, that you're then worried about missing data on the items that generated the two-mode projection or the one-mode projection of the two-mode data. In that case, I think that the good news there is there really are good missing data imputation techniques for things like survey data. So if we have a good reason to believe that if we can model the beauty of some of these big maximum likelihood missing data techniques, are that you can impute the entire covariance structure of the entire survey response structure from the covariance of all the other items on the survey response set. And the beauty there is that that's a much simpler problem, right? So whether or not a kid answered a question or not, or skipped a question on the survey, you can model that much more directly and then use that imputed data to generate your network. So I think in those kinds of situations where essentially you have you're constructing a network to help you understand patterns at a high dimensional level that are generated from a different kind of survey, you're better to go back to the old survey techniques for doing the imputation step there, as opposed to doing it on the network side of it, because the kind of complications that are built in there are just much more difficult. All right, are there general thresholds for how much complete network data you need to make a reasonable imputation?
70%.
Yeah, so the rule of thumb we used at Ad Health was 50% before we even computed any data. And I think that one of the nice things we've noticed in these missing data papers is that some things are remarkably robust to missing data of this sort. So you can end up with a very, something like 70% missing data, and still get non-meaningless correlations to your true values, particularly at the rank level. So
yeah, the community structure is like, it's actually sort of they have very low bias with lots of missing data. The flip side is that it's actually the imputation techniques don't recover all that much more. But on the other hand, the bias is already so low.
Yeah, so the bias is
so
low.
Bad.
And same thing with a lot of the network autocorrelation models. So the ability to recover, peer effects, given, if you're lucky and your data are missing at random, your models are almost going to be just perfect. Or you're going to have higher standard errors because you have lower information, but your coefficients will be really unbiased. So in that sense, like, there are types of missing data that are really non-problematic. And then there you can be missing like almost 70% of the data. The dyads you have tend to be, the same autocorrelated bit in terms of homophily kinds of scores that you would expect otherwise. So in that sense, from your absolute levels will be wrong if you're doing some kind of a rank score or percentage of kids or something. But the covariance structure, if you're going to use it in a model later, will be pretty accurate. So it's so in those kind of cases, it's there. Now, once you start looking at data that's not missing at random on the edges, so you have correlations with centrality, you have missing data based on one community as another. That is when then you need to find some way to model that non-random missingness in order to impute that accurately. And that's where it's really difficult. It just is.
Is there any final questions? Because I think we're 2 minutes or 3 minutes over time.
We are over, yes. So
I'm happy to talk to people in sideboard chat, or afterwards you can just email me. So
great. Thank you, John. Appreciate that. All right, so we're going to shift gears here now and move on to ergon models for bipartite networks. We're scheduled to start in 2 minutes. So let's just make sure Dave and I'll do bits here and make sure that he can get, that those guys can get hooked up and see where we're at. So.